Effective engagement in human society requires adapting, filtering information, and informed decision-making in dynamic situations. With robots increasingly integrated into human environments, there's a growing need to offload cognitive tasks to these systems, especially in complex, information-rich scenarios. We introduce multi-RAG, a multimodal retrieval augmented generation (RAG) system designed to assist humans by integrating and reasoning across video, audio, and text information streams. Multi-RAG aims to enhance situational understanding and reduce human cognitive load, paving the way for adaptive robotic assistance. Evaluated on the challenging video understanding benchmark, multi-RAG outperforms existing open-source video and vision language models while requiring fewer resources and less data. Our results highlight multi-RAG's potential as an efficient foundation for adaptive human-robot collaboration in dynamic real-world contexts. The relationship is both multifaceted and bidirectional. On the one hand, cognitive science has inspired the development of LLMs, informing architectures and evaluation methods that aim to mirror human cognitive processes. On the other hand, LLM's impressive performance on language, reasoning, and sensory tasks is reshaping and helping with how we think about intelligence and cognition. Let's begin with similarities. LLMs now match humans in word prediction and exhibit similar linguistic representations, even at the neural level. They also show human-like content effects in reasoning tasks and can correlate with human sensory judgments across multiple modalities, such as pitch or color. However, notable differences remain. LLMs display weaker inductive and statistical reasoning, and their performance drops with unfamiliar or novel tasks. Their functional linguistic competence is patchy, meaning they can struggle with context-dependent understanding and reasoning. LLM memory mechanisms are also quite different from human memory. These lead to several ongoing challenges. First, we need to enhance LLM's generalization capabilities, enabling robust performance beyond training data. Second, mitigating cognitive biases, like overconfidence or framing effects, is crucial. Finally, quantifying cognitive similarity between LLMs and humans remains a central scientific question. StreamMind, a state-of-the-art framework for real-time streaming video dialogue. Unlike traditional systems that process every frame, StreamMind uses an event-gated cognition approach, invoking the language model only when relevant events occur. This enables ultrafast processing, up to 100 frames per second, allowing the assistant to provide proactive and context-aware responses. As seen in these demos, the system can help users safely cross the street or guide them through cooking steps, responding at just the right moment. StreamMind paves the way for efficient, always-on AI companions in daily life. Memro, a wearable personal memory assistant developed by the MIT Media Lab. Memro is designed to help users retrieve important information in real time, especially during conversations, without causing disruption or anxiety. The system leverages large language models and advanced speech processing to continuously capture audio via a headset microphone. The captured audio is transcribed and organized as external memories, using natural language processing techniques for efficient retrieval. When a user needs to recall information, say, a name or a key fact, they simply click a trigger, and Memro infers the relevant query from the ongoing context. To minimize disruption, responses are concise, so the user remains fully engaged in the conversation. A user study showed that Memro not only reduced response times and improved recall confidence but also preserved the quality of interaction. Users stayed attentive and maintained natural eye contact. MaryQuery is an AI-powered educational assistant designed to provide trustworthy, course-specific support to both students and educators. By leveraging retrieval augmented generation, MaryQuery ensures responses are grounded in actual course materials, complete with source citations. The system offers granularity control, allowing instructors to scaffold learning or provide detailed solutions as needed. MaryQuery can process multimodal data, maintain chat history for monitoring, and support guided dialogue to enhance student engagement. Its research-driven design addresses academic integrity, transparency, and usability, making it a responsible tool for integrating LLMs into real educational environments. As you've noticed, both Memro and MaryQuery rely on a crucial retrieval step to provide relevant information to the language model. This retrieval process plays a key role in enhancing the capabilities of LLMs. Next, I'd like to introduce Retrieval Augmented Generation, or RAG, which formalizes and extends this concept as a core architectural approach. RAGs operate as follows. Knowledge base. Before retrieval, these documents need to be ingested and pre-processed, typically breaking down large documents into smaller chunks, transforming them to text embedding and storing them in a database. User query: the user asks a question. Retrieval: when a user asks a question, the retriever agents retrieve relevant information from our knowledge base to provide more context that will be incorporated into the prompt. Augmented generation: the LLM enhances its response based on the data retrieved. It allows the response generated to be not only based on pre-trained data but also relevant information from the added context. The retrieved data is used to augment the LLM's responses. The LLM then returns an answer to the user's question. We have implemented a graphical user interface to facilitate further experimentation. More than the video understanding, we add other useful functions with multimodal inputs. The top section features a function bar, providing controls for initiating or terminating speech recognition with real-time error correction, engaging in dialogue with the system, file management, video parsing, and summary requests. The main display area is divided into 3 columns. The left column serves as the dialogue panel, displaying transcripts of ongoing conversations. The central column is dedicated to the Q&A area, where system responses to user queries are presented, and the right column is devoted to video content, with the upper section offering dynamic or overall video summaries and the lower section presenting detailed video descriptions, including representative frames and associated audio transcripts. The bottom section of the interface allows users to select the response type and input questions, supporting both voice and text modalities. Inspired by the Real-Time Vision Assistant, our multi-RAG system for adaptive video understanding is designed to handle real-world, information-rich scenarios by integrating 3 main components. First, the video encoder processes both the visual and audio streams from incoming video. For visual data, a frame sampler intelligently selects frames. In environments like classrooms, where content is static, we filter redundant frames and focus on significant visual changes. In more dynamic scenarios, we use uniform frame sampling to ensure comprehensive coverage. Each sampled frame is then processed by a vision language model to generate descriptive texts and auxiliary metadata. Simultaneously, audio is transcribed into text using state-of-the-art speech recognition models like Whisper, allowing us to capture both spoken content and ambient context. Second, all these textual descriptions, transcripts, and metadata are formatted in Markdown file, then chunked and embedded into a unified knowledge database. This database leverages vector embeddings, and overlapping chunking ensures that contextual information is preserved for downstream retrieval. Finally, the RAG agent retrieves the most relevant chunks based on the user's query, using semantic similarity. These retrieved contexts are fed into a large language model, which synthesizes a rich, context-aware system answer, enabling timely, adaptive assistance grounded in multimodal understanding. RAG-LLM benchmarks fall into 2 main categories. First, text RAG QA benchmarks, such as natural questions and hotpot QA, evaluate a system's ability to retrieve relevant passages from large text corpora and generate accurate, concise answers. These focus on open-domain factual QA, using metrics like exact match and F1. Second, video QA benchmarks, like MMBench Video and Ego 4D, assess systems on multimodal tasks, requiring integration of video, audio, and text to answer complex questions. These tests measure not just answer accuracy, but also reasoning, perception, and temporal alignment. Together, these benchmarks provide a comprehensive evaluation of RAG-LLM capabilities in both textual and multimodal domains. The QA setting in MMBench Video Benchmark is structured around a 3-level hierarchical capability taxonomy. At the highest level, Level 1, capabilities are divided into 2 domains, perception and reasoning. These are further subdivided into 9 Level 2 capabilities, coarse perception, CP, fine-grained perception with single instance, FPS, fine-grained perception with cross-instance, FPC, hallucination, HL, logic reasoning, LR, attribute reasoning, AR, relation reasoning, RR, common sense reasoning, CSR, and temporal reasoning, TR. Level 3 capabilities consist of 26 fine-grained categories, capturing a broad spectrum of cognitive skills relevant to video understanding. Our evaluation results demonstrate several key strengths of the multi-RAG system. First, multi-RAG achieves a superior overall performance, reaching a mean score of 2.14. This is competitive with or even surpasses leading proprietary models like GPT-4o, despite operating at only half the input frame rate, showcasing its efficiency. In terms of reasoning capabilities, multi-RAG stands out by outperforming GPT-4o in the reasoning mean, achieving 2.21 versus 2.08. This reflects strong logic, attribute, and relation reasoning. When it comes to perception and hallucination handling, the system maintains consistently high perception scores and excels at mitigating hallucinations, particularly when using the second prompt design. Finally, multi-RAG proves to be robust and efficient, delivering strong performance even with fewer input frames. This makes it especially well-suited for scenarios where computational resources are limited or rapid processing is required. Augmented generation, Graph RAG, is gaining momentum and emerging as a powerful addition to traditional vector search retrieval methods. This approach leverages the structured nature of graph databases, which organize data as nodes and relationships, to enhance the depth and contextuality of retrieved information. Support multi-step reasoning and answering complex queries by traversing multiple nodes and relationships in the graph, increasing transparency, explainability, and trust in the system's outputs. Looking ahead, a key direction is multimodal retrieval. Rather than limiting AI to text-based information, future systems will be able to search and integrate images, videos, structured datasets, and real-time sensor feeds. For instance, a medical assistant could interpret X-rays in the context of patient histories, while industrial AI integrates sensor streams and maintenance logs. This multimodal approach promises more comprehensive, context-rich, and practical support across domains.